All right, so today I'm posting this video. It's a summary of reactions of organic compounds. That's going to be our focus this week, organic reactions. And I'm a little bit sad that we're doing this as remote learning because this is the part of organic chemistry that lends itself best to labs. So I'm gonna see if I can find some like dry labs online to cover some of this content. But for now, we're just going to do a quick survey of just a few examples of reactions that can happen between organic compounds. And the first reaction we're looking at is combustion, also known as burning. So we're just going to look at two examples of combustion. The first one is a straightforward complete combustion of a hydrocarbon in oxygen. Now, really, all organic compounds can combust. Just the example we're going to focus in on is a hydrocarbon. Okay, and this is a reaction that you've looked at before in grade 10 chemistry in unit 1 in this course, where a hydrocarbon reacts with oxygen to produce carbon dioxide and water. Okay, so an example of a hydrocarbon, we can stick with something really simple like just methane. Whoops, SCH4 is methane. Whoops, my bad. And then plus oxygen produces carbon dioxide, so CO2 plus water, H2O. Okay? There's a little typo here. This should say hydrocarbon. So this is going to be an example of an incomplete combustion reaction. You can see that word there, incomplete, distinguishes this from the reaction we just looked at. So an incomplete reaction, it's still got the same reactants, a hydrocarbon and oxygen. So let's say we'll do propane this time, C3H8 plus oxygen. But in an incomplete combustion reaction, you don't have quite enough oxygen for all of the carbon to end up as carbon dioxide. Okay, so you get some carbon dioxide, but you also get some carbon monoxide and some just pure carbon, which is what makes up soot. So if you burn something and it like is really smoky and leaves a lot of black dust behind, that means that incomplete combustion happened and you've got some carbon left behind. And then you'll also end up with water. Okay, you'll notice I'm not balancing these reactions. That's not the emphasis for this unit. Although if you wanted to practice those skills, you could go ahead and do that. But the emphasis here is really just representing different types of reactions. Okay, and then in terms of uses, combustion reactions are probably the most useful, well, maybe not the most, but the most commonly used reactions, or the most familiar ones. Burning is used for heating our homes. It's used for cooking. It's used to run our cars. So transportation. Okay, it's used in manufacturing, right? If you think of like, often you need to burn things or you need to generate a lot of heat in order to like melt things, or I guess melting is probably a big one, or just to get reactions going. So combustion reactions are very important in both industrially and in our own personal lives. Okay, and the reason they're so important is because anytime you burn a fuel like this in oxygen, you end up producing a lot of heat. Okay, and then that can be used to heat your home or cook or run the engine in a vehicle or to run machinery in a manufacturing setting. Okay. Next type of reaction is called an addition reaction. In these reactions, we take a simple molecule, something small like water or hydrogen chloride or the H2 hydrogen molecule, and we add it to something with a double bond. Okay, and it breaks up that double bond and makes it a single bond. You can also do addition on a triple bond. I'm not going to show you examples of that, but just know it is possible. So our first example here is an alkene plus halogen. So something like, I'm going to just draw a very simple alkene. So remembering that an alkene is something that has a carbon-carbon double bond. So this would be ethene. And I can add something, a halogen, something like, say, the chlorine molecule. And what happens is the chlorine molecule attacks the double bond here, so we end up with a single bond. We still have our hydrogens, but then to fill up those leftover bonding spots in carbon, we also add some chlorines. Okay, so it's called an addition reaction because I've added the atoms from this small simple molecule to my bigger organic molecule. Okay, this can work in a lot of ways. So I can also do an addition reaction with water. So something like, let's do propene here. Okay, plus water, H2O. And here, once again, my end of my molecule, this part, stays the same. But the double bond that I had here originally, it gets broken in an addition reaction. I still have all the same hydrogens I had before. But now I also get the atoms from the water molecule added onto my compound. So I might have an OH from one part of the water and then an H from the other part. Okay, so in addition reaction, we break a double bond. Okay, one more example of an addition reaction. This one's a little bit more straightforward. I'm gonna use ethene again just because it's easier to draw, because it's nice and small. So an addition reaction with another very simple molecule, the hydrogen molecule. Okay, and here we're still doing the same thing. We're breaking that double bond, making it a single bond instead. We keep all the hydrogens we had before, and then we just add 2 more hydrogens from the molecule we were adding. Okay. Now in the uses column here, these top 2 reactions, they're just sort of general tools for organic synthesis. Okay, so that's a very general term. It just means like organic chemists, so they might be manufacturing drugs, or they might be manufacturing plastics or other organic compounds, poisons or pesticides or whatever. They are often developing new molecules using different reactions, and an addition reaction is just like one of the tools that they have available. Okay? This addition reaction is also one of those tools, but it also has a kind of a more specific use. It's used in hydrogenation of fats. Okay? So you might at home have vegetable oil, like something like canola oil or olive oil or peanut oil. And you might also have at home something like margarine, which is a solid fat. Okay, so oils, when we talk about oils, we often think of things that are liquid at room temperature. And then solid fats are solid at room temperature. So things like margarine. And hydrogenation is actually how we take a liquid fat like canola oil and convert it to a solid fat like that we might see in margarine. Okay, so hydrogenation. So liquid fats usually have at least one double bond in their structure, whereas solid fats are usually saturated fats. They have only single bonds. And to convert a liquid fat to a solid fat, we can do this addition reaction, hydrogenation, and that gets rid of those double bonds so that the fat will stay solid at room temperature. And the reason this is done is because solid fats tend to have a longer shelf life. They just last a lot longer than liquid fats. They don't go rancid quite as quickly. So this has kind of been phased out because these fats, saturated fats, have been found to be worse for you than unsaturated fats. But especially in sort of the mid 20th century, a lot of manufacturing of foods included hydrogenating fats to make foods last longer on the shelf. Okay, I am going to pause it there and pick up with part 2 of this video talking about elimination reactions. Thanks for watching part 1.